Okay, I wanted to do one last video for session one about section 0.2 in the textbook. It's complicated, the coordination between these things. I want to talk about general and particular solutions to differential equations and the difference between the two, and sort of what you can expect in your attempts to get one from the other, if you know what I'm saying. Last time we talked about these two differential equations here. We talked about this y prime equals ky, and we found that solutions could be given by y equals c times e to the kx. And I asserted that this is what's called the general solution, meaning, one, that these are solutions, because you can plug them into this equation and they will satisfy it. But two, in fact, every solution to this differential equation is of this form. All right. So that's a sort of useful thing to understand. Every solution to this has this particular form. And similarly for this differential equation, y prime equals x plus 4. Not only is this a solution, every solution is of this form for some choice of this parameter or this constant c. Okay, you can make that c anything you want it to be, and it will be a solution. Not only that, but again, every solution is of this form. So if we're looking at, for example, this solution, which I'm asserting is a solution, and it is, this corresponds to when the c in the general solution is 0. So in fact, we give a name to solutions like that, which are not the general solution, but nonetheless themselves solutions. We call these particular solutions. Okay, so this would be the particular solution for this differential equation. And similarly, in the example above, we found this solution right here, e to the kx, where c, in this case, the constant c, which usually appears, is equal to 1. In this case, we call this a particular solution. It's a particular solution arising from the general solution by setting c equal to 1. This is a particular solution arising from the general solution when c is equal to 0. Okay? To see this in a little bit more detail, let's look at just one more differential equation. Let's look at the differential equation, and this one arises very often in the discussion of harmonic oscillators, so it's going to be of interest to us. And let's look at a second order equation. D squared y dx squared is equal to, let's say, negative k squared y. Okay, so k here is an arbitrary constant. It's fixed in the problem, so you can imagine it being 5 or negative 2. It doesn't matter. This is our differential equation. And I'm just going to tell you that the general solution, we talked about, this is going to be easy to see when we learn how to solve these differential equations. But for right now, just believe me that the general solution looks like y equals c1 times cosine kx plus c2 sine kx. So when I say this is the general solution, I mean that you can put any numbers that you want, c1 and c2, into this expression here, into this expression right here, into the general solution. And those will be particular solutions to this differential equation. Okay? Now, a good question is, what data do you typically need in order to pass from a general solution to a particular solution? That's going to come typically in the form of what are called initial conditions. So let's say that we have this differential equation, which is saying that the second derivative of y should be equal to negative k squared times y. Okay, let's say that we have that differential equation, but we add in the condition that, let's say, y of 0 must be equal to, I don't know, 3. Okay, let's say that we include that. And that y prime of 0 must be equal to 4. Let's just say that we have those conditions for our solution here. Okay, then we can say something about what C1 and C2 have to be. All right, so how? Well, if we plug in 0 here, so let me take this condition here and say, okay, y of 0 must be 3. That means that 3 must be what I get when I plug in 0 into this expression right here. If I plug in 0 into this expression right here, I get C1 times cosine of 0 plus C2 times sine of 0, right? Sine of 0, as you know, is 0, so this is, and cosine of 0, as you know, is 1, so this just ends up being C1. In other words, we get a expression for what C1 is. C1 must be 3. How about y prime being equal to 4? What does that tell us? Y prime of 0 equaling 4. Well, y prime of x in general, you will agree, is equal to C1k times sine kx, oh, with a negative sign, I believe, because the derivative of cosine is negative sine. And then this plus C2k times cosine of kx. Don't forget the k's because of the chain rule. Now we plug in 0. And that kills the sine term. That keeps the cosine term. And what we get is that y prime of 0, which, by the way, is specified to be 4, okay, is equal to C2k. Remember, sine of 0, this term, dies when x is equal to 0. This term survives, and it's equal to the C2k, because cosine of kx is equal to 1. So we're left with this. And of course, this tells us what C1 and C2 are. We learned here that C1 is equal to 3. And using this equation, that 4 is equal to C2k, we can infer that C2 is equal to k over 4. All right? No, I did that wrong. My bad. It's equal to 4 over k. There, I got it right. I just divided both sides by k. Great. So now we can write down the particular solution. And this is going to be, well, C1 is, we know what that is now. It's 3. So we're going to just replace in the general solution, which is right here, we're going to replace C1 by 3. And we're going to replace C2 here by 4 over k. So we learned that our final solution is y equals 3 cosine kx plus 4 over k sine kx. And what I'm saying is that this is the solution which not only satisfies the differential equation, not only satisfies this differential equation, but also satisfies these initial conditions. Okay, there's a lot moving here. So bottom line, if you're interested only in a differential equation and solving it, then what you're after is the general solution. But if you are further given initial conditions, as I am here, and these are called initial conditions, hopefully for obvious reasons. It's obvious because this sort of corresponds to what's happening when the parameter, the input is 0. 0 representing sort of the initial state of the system. When you are further given the differential equation, when you're further given, in addition to the differential equation, you're given these initial conditions, then you're looking for a particular solution, okay? And this particular solution is lacking the constants that you see in the general solution, okay? It's generally the case, going to be the case, that the order of the differential equation, the number of the derivatives, the number of derivatives that are involved in the differential equation will correspond to the number of parameters. Okay. Let me just say one more point, which is that, and then close this video. Sometimes you're given not initial conditions, but what are called boundary conditions. So let me give you an example of a boundary condition. So let's say that we have the same differential equation, but then the conditions that are further specified are not initial conditions. They are rather what are called boundary conditions, and they might look something like this. Y of 0 is equal to 3, so that's identical to what we had earlier, but we'll make a second condition that y of 4 is equal to 7. This is a different type of conditions, because a condition or set of constraints, because this no longer involves the derivative at 0, right? Up here, we saw the derivative at 0 being specified. Here, we're not specifying the derivative at 0. We're instead specifying the value of y at 2 different points, okay? And these are called boundary conditions. Oh, I should write it in ink is not the right word for whatever this is. And you can use, I hope, the logic that we used in the previous problem to figure out the constants C1 and C2 from these boundary conditions. I hope that makes sense. Okay? All right. So I'm not going to do that here and now. In fact, I strongly suspect that this will not have necessarily solutions. This sort of ends up corresponding to, well, I don't need to get into it, but this corresponds to some very important considerations in quantum mechanics, believe it or not. Okay, things like this problem of a particle in a box. Anyway, this is all way too interesting to talk about, and this video is a little bit long, so I'm going to end it there. But hopefully these first 3 videos are giving you a little bit of a look into how differential equations kind of look. Okay, that's enough.